Okay, welcome to the third lecture of Unit 3. In this lecture, we are going to talk about observers. This is in continuation to what we have learned about pole placement in the previous two lectures. Just to revise what we did as regards pole placement, we saw that we could use a state feedback law u is equal to minus kx to place the poles of any plant which is controllable anywhere, right? And we did this using two methods. One method was when we had the system in controllable canonical form, and we could just compare the coefficients of the desired and actual characteristic equation. So you could just compare the coefficients and find out the values of k. This was the first lecture, and the second lecture we saw that we can compare the determinant of a minus bk with the required characteristic equation to get the value of k. We also saw a transformation that converts a system to controllable canonical form, and this transformation can be used to apply the first method here. So you can convert a system to controllable canonical form and apply this transformation to do that, and then find the value of k after the system has been transferred to controllable canonical form, right? So there's one more way of doing it, which is called the Ackermann's formula, and it is actually derived from this transformation to controllable canonical form. So we're not going to derive the Ackermann's formula. I'm just going to tell you what is the formula. So if you have an nth order system which has the form x dot is equal to ax plus bu, it's a seesaw system, and a belongs to n cross n, and you want to control it, and you want a desired characteristic equation in the sense you want particular places where your closed loop poles should be, and the desired characteristic equation is s to the power n plus alpha 1 s n minus 1 plus so on and so forth alpha n minus 1 s plus alpha n is equal to 0. If this is your desired characteristic equation, then the Ackermann's formula says that the k matrix that you want to find out is going to be 0 0 all the way n terms up to 1, then u inverse phi a. What is u? U is the controllability matrix b a b a to the power n minus 1b. And what is phi a? Phi a is the matrix A put in the characteristic equation. So put the matrix A in place of n in the characteristic equation. So you get a to the power n plus alpha 1 a to the power n minus 1 plus alpha 2 a to the power n minus 2 plus alpha ni. So what it actually means is that if you have an n order system given by x dot is equal to ax plus bu, it is seesaw, and you have a desired characteristic equation given like this, then your K matrix would be this, right? Where the U term is the controllability matrix and the phi is actually the A matrix put in the desired characteristic equation. So it's a simple formula, but it actually comes from the transformation that we saw on the last turn that converts a system to controllable canonical form. We'll solve some questions related to this when we do the tutorial for the third unit. You can see some of the solved examples in the book that I have uploaded on the classroom web page. So continuing this, as I told you in the beginning, that our topic for this lecture is observers. Now, what do you need to implement the control feedback, state feedback u is equal to minus kx? You need the information about x, you need the information about states. And normally in your closed loop system, the information about the states may not be available. And why is that? It is because states are actually internal variables which determine completely the behavior of all other dynamic variables, right? As we saw in the beginning, when you defined states, we saw that they were a set of variables which you could use to find out any other dynamic variable of the system at any time if you knew the states and you knew the initial conditions and you knew the input that you're applying to the system. So these are actually internal variables, and some of the states are combined, or all of them may be combined, to give you the output y. And that you see in the algebraic equation y is equal to cx plus du. So what is available for measurement, if this is your system, you're giving it the input, it is responding with this input, it is responding with y, and there is this dynamics inside the system. It's a dynamical system, things are changing with time, and that change is actually incorporated in x, but this x is not available for measurement. What is available for measurement is y. And what is y? Y is just a linear combination of the x's. So you may have all the states, right, for measurement available, especially simply because if you see an identity matrix, then y is equal to x, and then you could have all the states are equal to the outputs and you would be able to measure. But normally this is not the case, especially for higher order systems in which n is large. You will not have all the states for measurement. And we have seen in the examples that we have seen single input, single output systems, right? So the output is just one variable. It's a linear combination of some of the state variables. So x is not available for measurement. What do you do with this now? If x is not available for measurement, how can you apply the state feedback law, u is equal to minus kx? Because you need x, the information of x, to be multiplied with k, and that gives you the input that you have to give to the system in order to place the poles wherever you want to place them. So the solution is to design an estimator or an observer. So what is an observer? What is the definition of an observer? So an observer is a device or a computer program that estimates the state variables of the plant. So you don't measure them, right? There is no measurement, right? This is very important to understand the difference. there is no measurement of the state variables. In the sense, you don't have any sensors that you can couple to the plant to measure all the state variables, but you have an estimate. And what is this estimate? How is it going to work like? I'll give you an example. Suppose you have a plant. And you have the A matrix, you know the A matrix of the plant, you know the B matrix of the plant, you know the C matrix of the plant, and you are giving it an input, and you know the initial conditions, right? And you see the output Y. Suppose because you know the A, B, C and the initial conditions, you give the same input to a computer simulation, a computer program, which basically simulates your plant. And you feed in the matrices A, B, C, you give in the initial conditions x0, and you get this Y. We call this Y hat, right? So basically you have the information of all the states inside this. We call them X hat, right? And as your plant responds to this input and the state variables X change, so similarly your computer simulation would respond to the input and the states X hat would change. And if your estimate of A is good, if your estimate of B is good, if your estimate of C is good, if your basic knowledge of these things, not estimate, these knowledge of A, knowledge of B, knowledge of C, knowledge of x0 is good, then what will happen is that your X would be exactly followed by X hat, right? So, and then you can use this X hat, because this X is not available for measurement, but this X hat is in your control. It's a computer program, so you know at all times what is X hat. So then you can use this X hat to make the state feedback law U is equal to minus K X hat, and this will be almost equal to minus Kx, because the program and the ABC matrices are same. So basically this is called an open loop estimator. And the better way to draw this is something like this. You have an input going into a dynamic system, x dot is equal to ax plus bu, and you get x out of this, multiply this with c, get y. The same input goes into, this is your plant, this goes into your model or your simulation, right? And you say this is x hat dot is equal to ax hat plus bu. This gives you x hat, multiply this with c, you get y hat. So this is an open loop estimator. You give it the same input and it responds to the same input in the way the plant responds, and this plant responds, and you are able to get an estimate x hat. So x hat is the estimate. And the good thing is that x is not measurable, but x hat is measurable, is in your control. It's measurable. It's an estimate. It's an estimate of x. Now there is a problem with this open loop estimator. The problem is that if your knowledge of x, it relies on the fact that you have accurate knowledge of A, B, C, x0. And especially you have accurate knowledge of x0. If the knowledge of x0 is wrong initially, even by a little bit, then your x hat and x would diverge. And this is very obvious because the initial conditions, your system starts behaving onwards from the initial conditions, right? And even in the state equation, you see that your x0 is present. If you remember, the state equation solution is equal to phi t x0 plus this integral term 0 to t phi t t minus tau b u tau d tau. So this phi t term is present here. This x0 term is present. So if this initial estimate of x0 is not right, then what happens is that your x hat t, which would actually be phi t, if your phi t is from x, then this estimate initial x0 is different. Say this is x bar plus 0 to t phi t minus tau b u tau d tau. Then this difference in this term is going to be compounded. It's going to increase as time proceeds, and finally your xt and x hat t would have a large difference. So there will be a large error in the estimate of xt. This problem can be solved using an observer mechanism, which is called the Leuenberger observer, and we'll see this in the second lecture of this second part of lecture 3. Thank you for now.